Okay, I'm continuing on in our discussion of molecular geometry here and figuring out the shapes of these molecules based on the Lewis structure we prepared. Right? And we've reached the last one here, or at least the last set, and that would be 6 sets of electrons. Now certainly molecules can get more complicated than that. If you can continue on studying chemistry and you go on to take something like inorganic chemistry, where you start to talk about transition metals, or even lanthanides or actinides. You have really large molecules, lots of available orbitals. You can certainly have more than 6 bonds connected to a central atom, and you can lead into even more complicated things. But for our purposes here, our understanding of bonding, we can kind of cap things at 6. So what if there are 6 sets of electrons? There are certainly possibilities here. They could all be bonds, so 6, 0. We could introduce a lone pair, so 5, 1, right? And we should at least consider 4, 2, 4 bonds and 2 sets of non-bonding electrons here. Okay. Now, the point drawing, if we have 6 things, right, and they need to spread as far apart as they can basically go to the corners of a set of coordinate axes. So this will actually look sort of like the coordinate axes you might know from something like algebra. One pointed up, one pointed down, is your z-axis, right? One to the right, one to the left, right? And then the other axis would be kind of straight in and out of the piece of paper, right? So I'm going to draw that, I'm going to off at an angle, right? But that would be kind of what your structure would look like, right? This is called an octahedral. And it's called an octahedral because of the shape that it makes, right? There are 6 bonds there. People will confuse that occasionally and think, well, there must be 8 bonds, or they'll think there's 6 bonds. I'm going to call this a hexahedral. And a hexahedral is a cube. This is an octahedral because if you were to connect all the outsides here, you would make a figure with 8 sides. So if anybody has played Dungeons and Dragons or something similar, right, an 8-sided die is an octahedral that you would roll, damage from your club or something like that. So this is an octahedral shape. The bond angles here are all 90 degrees, right? Just like the angles between the x-axis, the y-axis, the z-axis in a coordinate system, right? Or negative x, negative y, and negative z as well. The molecular geometry, at least when they're all bonds, is the same. So this is an octahedral shaped molecule as well. And an example here, right, a central atom that can make 6 bonds, that would be something like sulfur. So if we take a sulfur and connect it, say, with 6 fluorines and get SF6, we could connect all 6 of those fluorines around that sulfur, and that would make an octahedral shape. Now, we should have lone pairs around all those fluorines. I'm just going to leave it like that here, but keep that in mind. If we're really drawing this and not limited to this tiny amount of space that I have there at the end of my page, right, we should have lone pairs on all of those fluorines. Okay. Now, what if we take away one of those bonds, but we replace it with a set of non-bonding electrons to make the 6th set? Now, there's a lot of symmetry here in the octahedral, so it doesn't really matter where you choose to put the lone pair because every position is the same. So a little different than with the trigonal bipyramid that we looked at before. So in terms of drawing, I'm just going to put the lone pair on the bottom position. That means the other 5 pretty much stay right where they are. That one will stay kind of pointed straight up. These will stay in the plane, right, sort of equatorial plane here. And then the lone pair will kind of be there, occupying that bottom position. Now there's still 6 sets of electrons. As far as where the electrons are, this is still octahedral because that 6th set of electrons or lone pair is still being counted, right? And that means 90-degree angles. Now you might also say 180 here, right? If you're looking at 2 across from each other in equatorial positions. You could certainly do that back here as well, but you'd kind of be going by another atom in the process. Now, what is the name of the shape here, or the molecular geometry? These four in the kind of equatorial plane, the way I drew it, are basically a square, right? And if we kind of draw lines up to the one pointed up here, that would make a pyramid, but a pyramid with a square bottom instead of a triangular bottom. So the other pyramids we saw were triangular pyramids or trigonal pyramids. This one is a square pyramid. So this is called square pyramidal. And I've seen this written as square based, like square dash based pyramid, because it's a pyramid with a square base, right? But usually I just see this as square pyramidal, or that it's a square pyramid in shape. Now, how can we get to this one? We need a central atom here that could make 5 bonds and still have a lone pair. So got to be big enough to go past the octet. And it'd be neutral if it had 7 valence electrons to start with, because 7 minus 5 minus 2. So that would be something from the halogen column, or column 17. So let's use iodine, since that's the biggest one, would be the best central atom. And maybe we attach 5 chlorines to it, right? That would mean iodine goes in the middle, right? And again, I'm drawing this because we already know this is the shape. That is probably not the case if you're doing a problem where you're just given the formula and you have to draw it and then figure out the shape. So keep that in mind. You might have this drawn flat, right? But ICl5, that'd be 42 electrons, since each one comes with 7, right? We use 10 for the bonds, that leaves 32, but we use 30 to complete the octets on the chlorines. So there's 2 left. That would be the lone pair on the iodide, and that would be a square pyramid shape for the molecule. Okay. Now for 2, we're going to add 1 more lone pair. Now, if we think about adding a lone pair to our previous structure, right, there are choices that would lead to different geometries. But lone pairs, it turns out, don't like each other a whole lot. So the next lone pair, we want to put it as far away from the first lone pair as possible. So since I drew the first one kind of on the bottom of the structure, the second one should go on the top. And that means we only get one structure. The lone pairs will always be opposite from each other in this type of structure. So we'll have these 4, right, that are still in that plane in sort of a square position. And there'll be 1 lone pair up there and 1 lone pair down there. And electron-wise, this is still octahedral. There are still 6 sets of electrons that are arranged around that molecule. Right? Your bond angles here are still 90 degrees and or 180 degrees. But as far as the shape, right, this now is a square. We've eliminated kind of the third dimensions by taking away those atoms. So this is called a square planar molecule. So usually you don't just say square. I've never seen this called a square-shaped molecule. It's a square planar molecule. Right? And I think that's useful because we are distinguishing between the square pyramid and the square planar. So don't just say square. It would be hard to know which one you intend. Right? And don't just say pyramid, because there's a square pyramid and a trigonal pyramid. So make sure that you're kind of explicit in your names. Now, how would we get here? 4 bonds, 4 non-bonding electrons, right? One way to get here is, and have no formal charge, would be to start with something with 8 valence electrons. And we can do that. You can take a inert gas, noble gas like xenon, and you can actually force it to react with really electronegative elements like fluorine and oxygen if you create the right conditions. So you can make a molecule that has a xenon as the central atom and has 4 fluorines attached to it. If we go to draw that structure, so well, let's count the electrons. 8 for xenon, 4 times 7, 28 for the fluorines, so that's 36 total electrons. But if we put the xenon in the middle, and let me just draw it flat here. That would use up 8 of the electrons connecting the xenon to the fluorines. That would leave 28. Well, that's enough to give 6 to each fluorine, right? We have 28. It would be 24 to give 6 to each of the 4 fluorines. That would leave 4 electrons, and those 4 would have to go on your central atom. Now, xenon is a big atom. It's big enough that you can have that many electrons around it, right? But again, if you drew this structure, you would look at it and you go 1, 2, 3, 4, 5, 6 sets of electrons. That's an octahedral electron geometry, but 2 of them are lone pairs. The shape is going to be square planar, okay? Now, you could get here with ions as well, right? If you have a halogen in the middle, something that starts with 7 valence electrons from column 17 of the periodic table. If you give it 1 extra electron, you would get here too. So you could do this with kind of an iodine compound as well. So say you took an iodine and 4 chlorines but made it negative, you would get the same structure. Iodine in the middle, 4 chlorines. In fact, that 1 extra electron is just enough to get you to the same count of 36. Right? And if you have the same set of atoms or same number of atoms and the same number of electrons, you're going to end up at the same structure. So that would have a negative charge. The formal charge would be on the iodine there, but that would get you to a square planar compound as well. Okay, there's not any real good way to get to 3 and 3 with the types of atoms we've talked about. You can do that with a transition metal. You could get to 3 bonds and still have 3 pairs of non-bonding electrons, right? If you're using some of the d orbitals that would be available when you have a transition metal. Okay, that really wraps up just determining the shape and the angles. The next thing we need to think about is using the shape and the angles to determine whether or not a molecule is polar or non-polar, and we'll do that in the next video.